In this exercise, we'll take a look at multi-class text classification. The dataset that we'll use contains complaints about financial products and services. What we'll try to do here is predict which category any consumer complaint narrative belongs to. A first step is to look at a summary of the dataset. It contains over 900,000 entries, each of which has 18 columns. We're really only interested in two columns, product and consumer complaint narrative. In the product column, we have 18 possible values, from credit reporting down to virtual currency. What we want to do here is remove missing entries in the consumer complaint column. We also want to just keep two columns, product and consumer complaint narrative, and we want to rename consumer complaint narrative to just plain old narrative. This leaves us with two columns to which we add a category ID. This column encodes the product as an integer because categorical variables are often better represented as integers rather than strings. After cleaning up, we see the first 5 entries in our new data set. From this plot, we can get a feel for the number of complaints in each product category. We can see that the number of complaints per product isn't balanced. Consumers' complaints are more biased towards debt collection, credit reporting, and mortgage. Classifiers and learning algorithms cannot directly process the text documents in their original form, as most of them expect numerical feature vectors with a fixed size rather than the raw documents with variable length. Therefore, the texts are converted into a more suitable representation during a pre-processing phase. One common approach for extracting features from text is to use the bag of words model. This is where, for each complaint narrative, the occurrence and frequency of the words is taken into account, but the order in which they occur is ignored. For this exercise, we will calculate a measure called term frequency inverse document frequency, abbreviated to TF-IDF for each term in our data set. To do this calculation, we will use a TF-IDF vectorizer to return a vector for each of the narratives. The vectorizer takes the following parameters: sublinear TF to apply sublinear TF scaling. This is motivated by the observation that 20 occurrences of a word do not indicate 20 times the relevance of that word. MinDF, i.e. minimum document frequency. So this is to ignore terms that have a document frequency lower than the threshold given by MinDF. Norm. This is used to normalize term vectors. It is set to L2 to ensure all feature vectors have a Euclidean norm of 1. Normalizing lets us consider the frequency of words relative to each other while removing the effect of the total word count. N-gram range is set to 1, 2 to indicate that we want to consider both unigrams and bigrams. Stop words is set to English to ignore all frequently occurring tokens, such as articles and pronouns, to reduce the amount of noise in a dataset. The fit transform method returns a TF-IDF weighted document term matrix in which each of the 200,000 odd narratives are represented by 200 odd thousand features, which represents the TF-IDF score for different unigrams and bigrams. Next, we use the chi-square test to find the terms that are most associated with each of the products. A chi-square test is designed to analyze categorical data. That is, data that has been counted and divided into categories. The chi-square test is intended to test how likely it is that an observed distribution is due to chance. Below are the product labels together with the most correlated unigrams and bigrams for that product. Looking down, we can see bank, account or service is correlated with the unigram bank and overdraft, and bigrams overdraft, fees and checking account. If we look to consumer loan, we can see it's correlated with car and vehicle as unigrams and car loan and auto loan as bigrams. Credit card is correlated with Macy and card and American Express and credit card as bigrams. Credit reporting has Experian and Equifax as unigrams and TransUnion and Credit Report as bigrams. These are much the terms we'd expect to be correlated with those product categories. To train a supervised classifier, we must first transform the narrative into a vector of numbers. With this vector representation of the text, we can train a supervised classifier on unseen consumer complaint narratives and predict the product to which they belong. With the data transformed and all the features and labels in place, we can train the classifier. There are a number of algorithms we can use for this type of problem. The one we use here is the multinomial variant of naive Bayes classifier. This classifier is suitable for classifying data with discrete features, in this case word counts for text classification. The multinomial distribution normally requires integer feature counts. After fitting the training set, we can make some predictions, as will follow. Here we test our classifier on some sentences extracted from our dataset. As you can see, they're broadly accurate, but some stand out for not being so. So, debt collection, I would have thought, belongs to student loan. Here, I have no money to pay my tuition. And here, Coinbase closed my account, etc. That's predicted as debt collection. I would have thought that would be virtual money. But this one here is correctly classified as debt collection, and the one below correctly classified as credit reporting. Here we experiment with different machine learning models and evaluate their accuracy and find the source of any potential issues. So the ones we try are random forest classifier, linear SVC, multinomial naive Bayes, and logistic regression. From the box plot, we can see that linear SVC is the best performing, and we can see that in the score here. Now we're going to look at a confusion matrix, which shows the discrepancies between predicted and actual labels. Here we use a linear SVC to produce a test and prediction set that will serve as input to the matrix. Remember, the linear SVC was the best performing of the models we tested. The vast majority of predictions end up on the diagonal, as we can see here. which is where we want them to be. However, there are a number of misclassifications, and we will be able to see them here in this table. As you can see, some of the misclassified complaints are complaints that involve more than one subject. Like, for example, complaints involving both credit card and credit report. Here I've just actually included the most high counting report anomalies. So the count you can see here is the number of anomalies for credit reporting against consumer loan. Here we predicted 759 to be debt collection, whereas actually they were credit reporting. This table is actually considerably longer, but we filtered it just to have more than 100 counts of anomalies. Here we run the same tests as we did earlier, but this time using the linear SVC as the model to predict. The outcomes are improved. For example, I can't get my money out of the country comes back as money transfers rather than debt collection. We can see the narrative beginning with Coinbase now has a correct classification as money transfer, virtual currency or money service. So the accuracy is much improved in this model. Finally, we end this exercise by looking at a classification report which provides a breakdown of metrics. We will start with the precision score, which includes true positives and false positives. Precision means accuracy of positive predictions, i.e. true positives over true positives plus false positives. The recall score is about false negatives. So this is the fraction of positives that were correctly identified, i.e. true positives over true positives plus false negatives. The F1 score, also known as F-score or F-measure, is a helpful metric for comparing two classifiers. F1 score takes into account precision and recall. It's created by finding the harmonic mean of precision and recall. Finally, support is the number of samples of the true response that lie in that class.